Okay guys, as I'd promised, I'm going to make a video here. This will be the first of hopefully two videos in which I do some sample Newton's laws problems, so some problems involving Newton's three laws. This video I'd like to do three relatively straightforward problems. I won't call them easy, but they're relatively straightforward, and then hopefully I'll have a chance to make a video where I'm going to do three more involved problems, tougher problems. So let's get started. Let's see. Let's try this. So here's a frictionless surface. Here it is, frictionless. And I have two blocks on that surface. So here's one block, and connected, not connected, but adjacent to, touching the first block is a second block. So maybe we can call this guy right here. This will be M1. And then maybe just so we don't get confused, I'll do M2 in a different color. So, and then here's M2. Right next to it, touching M1, is a second block. And this guy here, this is M2. And so let's give these some values. Let's say that M1 has a mass of, I don't know, let's say it's 2 kilograms. Or actually, let's make it 5 kilograms. And let's say that M2 here has a mass of 10 kilograms. And what I want to imagine is if these two blocks are touching one another, I want to imagine what would happen if I pushed right here with a force F, where the force applied here, F, is going to be a force of 30 newtons. And the first thing I'd be curious to know about is if I push right here, what is going to be the acceleration of the system. And so what do I mean by the system? Well, clearly the system is the two blocks, right? The two blocks are both, M1 and M2 are both going to slide to the right. They're going to accelerate to the right because there's no backwards countervailing force. There's no force resisting the forward pushing force. I should note right away, I think this is obvious, but I don't have to worry about vertical forces, right? There's going to be gravitational pull on M1 and M2, but the normal force upward is going to cancel them out. So maybe I'll just put that in here. There's going to be a gravitational force here and here, but that is going to be canceled out in both cases by a normal force. So there's going to be a normal force N and a gravitational force. This is M1G and this is M2G, and these are going to cancel out, so they're irrelevant. So from now on out, from this point on, I'm going to ignore those vertical or y forces and just think about the horizontal forces. So what's the acceleration of the system? Well, the acceleration of the system is we take F net equals ma. So I can say the acceleration of the system is the net force divided by the mass. So the acceleration of the system then is going to be the net force, which in this case is just F, 30 newtons, divided by the total mass of the system. And since both blocks have inertia, this is 15 kilograms. And so the acceleration is therefore 2 meters per second squared. Fairly straightforward problem. The net force is just this applied force because there's nothing working against it. And then the total mass is 15 kilograms. All right, so that's the first part of the problem. The second question I might ask is, what is the force between the two blocks? So find another color here. There's going to be some sort of a contact force between these two blocks. In other words, M1 is going to push on M2 this way, right? There's going to be a forward force. This is F1 on 2. This is the force of M1 on M2. It's a contact force. And of course, what's going to happen if M1 pushes on M2? Well, M2 is going to push backwards on M1. And these two forces, these two here, have to be equal. That's Newton's third law. If M1 pushes on M2, M2 pushes equally back on M1. All right, so I'd like to know what is the magnitude of this force, this contact force between 1 and 2. What is that F1, 2? And so right here, you might look, if you looked at this right here, you might naively think that this has got to also be 30 newtons. You might say, well, if I push on M1, M1 pushes on M2, it's going to be the same 30 newtons of force. That would be wrong. And hopefully you can see why if this force were 30 newtons, M2 would not be accelerating at 2 meters per second squared, right? It would be accelerating at 3 meters per second squared, which it's not. So how can we calculate that force? Well, what I can do is I can say that this, I can change my system, and I can say that this force, this is the net force on M2. So F net on M2 is F12. So F12, this F right here, that is the net force on the system M2. So now I can say this F12 is MA, M2A. And I know M2, it's 10 kilograms. And I know the acceleration experience is 2 meters per second squared. So this is 10 times 2, or 20 newtons. So this force is 20 newtons, not 30 newtons, 20 newtons. And I know that because I know that this is the net force on M2, right? I can't cancel it with this force here, right? I can't cancel because these two forces are equal and opposite, but they're on different objects. They don't cancel. This is the net force on M2, and I know M2's mass and its acceleration. Let's think about that. That means that this force right here is also 20 newtons. Does that make sense? Well, what is the net force then on M1? Well, M1 has got maybe it's worth drawing M1 here. Here's M1. That's terrible. This is M1 in isolation. And what are the forces? Well, there's M1G down, normal force up. Those cancel, right? I know these are equal. Then I've got this pushing force, this 30 Newton force forwards, and I've got this now, this force right here is 20 newtons backwards. So what's the net force on M1? Well, the net force on M1, F net M1, is just 10 newtons. Does that make sense? Well, it has a mass of 5 kilograms, and it's accelerating at 2 meters per second squared. MA, 5 times 2, is in fact 10. So that checks, that makes sense. Okay, I went over that in excruciating detail, but hopefully, if you didn't understand that, hopefully you do now. Okay, here's another problem, similar in nature, but a little bit different. We've got an elevator. Here's an elevator. This is the cab of the elevator. Right, so there's some sort of a cable here, so this can accelerate up or down. And inside the elevator, for some reason, we have a bathroom scale. And then on the scale is some person here. There's a person standing on the scale. And the person, the mass of the person is, let's make it just 100 kilograms. And then there's a reading on this scale. The scale is going to read something, right? And it might be worth wondering or thinking for a moment, what does the scale read? And you might think to yourself, well, it reads your weight, which is, if you think about it, nonsense. The scale doesn't read your weight. In fact, the scale knows nothing about your weight. All the scale knows is how hard it pushes on you. So if I stood on a scale in an elevator here, it might not read my weight depending on the way this elevator is moving. The reading of the scale is gonna fluctuate depending on how the elevator is moving. Or maybe to think about it even more basically, if I stand on a scale and start jumping up and down, the scale reading fluctuates as I bounce up and down. That doesn't mean my weight is changing. It simply means that the force of the scale on me changes. So what does the scale read? Well, the scale reads this upward force. That's the normal force. N. I'm going to use N for normal force. So the reading of the scale, the normal force, N, let's say in this problem is 700 newtons. So this is the scale. That's the scale reading. Is the normal force. It knows how hard it pushes up on you. And the question is, what is the acceleration of the elevator? What is the acceleration? That's what we'd like to know. Okay, well, how do I approach this? Well, I do know that this person, I know that the normal force is 700 newtons. And I know that this person has a weight, mg, downwards, which is 100 times 9.8 or 980 newtons. So I know that the net force, F net, is going to be 980 minus 700 or 280 newtons. That's this force minus this force. Gives me 280 newtons. So what's the acceleration then? Well, the acceleration, F equals ma. A is F net, 280, over m, which is 100. So I end up with an acceleration of 2.8 meters per second squared. Well, in what direction is this acceleration? Well, it should be clear to you that 980, since it's more than 700, it's going to be down. You might say negative 2.8 meters per second squared, or 2.8 meters per second squared down. So this is, again, this is a Newton's third law argument in some senses, and it also introduces the idea of what you might call apparent weight. This scale reading here is sometimes called the apparent weight. Because the scale apparently reads 700 newtons, meaning you apparently weigh 700 newtons, which of course we know you don't. In fact, you could think about it this way. What would happen if, like, the cord here were cut? You could imagine if, like, this cord here were cut and this thing entered free fall, what would the scale read? It would read 0. You would apparently be weightless. Of course, you're not weightless, but the you appear to be. All right, last one. Atwood's machine. We've talked about Atwood's machines before. This is an Atwood's machine. We've got a pulley here fixed to some ceiling, some immovable object. And I've got two weights hanging. Here's one. Call this M1, and we'll say it has a mass of 2 kilograms. And here's M2, which has a mass of 3 kilograms. And this, now I'm going to ask, what's the tension in the rope? What's the tension in the rope? Find the tension. So that's our task. Now the first thing I'm going to say is, let's think about the tension in the rope. Well, everywhere along this rope, the tension has to be the same. It has to be the same everywhere. And the reason for that is that if the tension varied from element to element throughout the rope, if that were to happen, then the different pieces of the rope would be accelerating at different values. And that's not allowed. If that were happening, then the rope would break. And assuming that the rope doesn't break, then the tension has to be everywhere the same. By the way, when I say this, when I say that the tension must be the same everywhere, when I say this, constant tension, the assumption underlying that is that it's a massless rope. Or at least it's negligible mass, because certainly the rope has to support its own weight, and so if the rope had mass, then the tension would change, and that would be very difficult to deal with. So we're going to imagine for right now that it's a massless rope. Later on, we're going to have to talk about the fact that this pulley has to be massless as well, but let's not get ahead of ourselves. So we're assuming a massless rope, a massless pulley, and we've got M1 and M2 here. And the question is, what's the tension? And we said the tension has to be everywhere the same, because this rope, the entire rope, has to have the same acceleration value. Which means that the rope is pulling up on M2 with a certain tension value T, and it's also pulling up on M1 with the exact same tension value T. Since the tension is everywhere the same, these two have to be equal. The question is, what is that tension? So the first thing I want to think about is, in order to find the tension, it might be helpful. In fact, it's necessary that I figure out what the acceleration of the whole system is. So what's the acceleration of the whole system? Well, the whole system is this thing here, inside the blue figure. This is my system, M1 and M2 taken together. So the tension forces are internal to that system, and they don't matter. So if I want to know the acceleration of the system, the only forces that matter are M1G and M2G. Those are the only forces that I care about, because since I'm thinking about the entire two-mass system, these tension forces are internal, they're irrelevant. So the net force, what is the net force then? Well, the net force is going to be the difference between M2G and M1G. Even though both of these arrows are pointing down, don't be tempted to add them. They're oppositional, they're fighting one another. So the net force is just going to be M2G minus M1G, which is going to be 2 times 9.8, or sorry, 3 times 9.8 minus 2 times 9.8, or simply 9.8 newtons. So the acceleration then is 9.8 newtons divided by the total mass, which is this 5 kilograms. What's that going to be? 1.96 meters per second squared. So that's the acceleration of the entire system. Well, that's all well and good. And by the way, it's going to go this way, right? The acceleration is going to go this way. The acceleration here is down, and the acceleration here is up, right? Because M2 is bigger than M1. All right, so how does that help us find the tension force? Well, now we have to change our system. I'm going to change the system now, and now I'm going to think about just M1. You could think about just M2, but I'm going to think about just M1. This is my new system. And in this system, the tension force is not irrelevant. It's an external force if I think about just M1. In fact, it might be easier for me to just draw M1 in isolation. So here's M1. Free body diagram, M1. Well, if my system is simply M1, then there are two forces. There's the tension force, and there's M1G. Are these equal and opposite? Well, no. They can't be, because this thing is accelerating upwards at 1.96 meters per second squared. In fact, I should be able to calculate the net force on M1. The net force here, F net, should be M1A. M1 is 2 kilograms times the acceleration of 1.96 here, right? That would be our net force. This would be 2 times 1.96. And what is that? How do I get this net force? Well, look at it. The tension force is up. M1G is down. Which one is bigger? Well, this is accelerating. The acceleration is up, right? Go back to this picture. It's an upward acceleration, meaning the tension force must be bigger than M1G. So this 2 times 1.96, this net force, another expression for it, must be the tension here minus M1G. So in other words, this 2 times 1.96 must be equal to the tension force minus M1G. And now I can go ahead and calculate the tension force. So I say 2 times 1.96, the net force, equals tension minus 2 times 9.8. So now I get that the tension here is 2 times 1.96 plus 2 times 9.8, which gives me 23.5 newtons. These tension problems can be tricky. I think the part that's tricky is that you frequently have to do this. You have to alter what you think of as your system in the middle of the problem. Initially, we computed the acceleration by looking at the entire two-block system. And in that system, the tension forces were irrelevant. And then, to calculate the tension force, we had to change the system. We looked at M1 in isolation. And in doing that, now the tension force is not irrelevant. It's part of it's external to the system M1 and is therefore relevant. I want to note you could go through the entire same argument, but look at instead, we could have chosen the system to be M2. Right? We could have used that as our system. If we had, it would have been very much the same argument. What would have been different is that now M2G would be bigger than the tension force. So what would that look like? I'm running out of space. Maybe I'll move over here. If we'd done that, if we'd instead looked at M2, then I would say the F net is M2A, and that is the result of these two forces, tension up and M2G down. But now I would say that this net force, M2A, the net force, is equal to M2G minus T. Right? Over here, I didn't do that. Over here, I said that the net force is tension minus M1G because the tension force was bigger than M1G, but here it's not. In this case, since M2 is accelerating downward, right, there's a downward acceleration as far as M2 is concerned, so I say M2G has to be bigger than the tension force. So now the tension force is going to be M2G minus M2A. So that's, what is that, 3 times 9.8 minus 3 times the acceleration of 1.96. And if you do that out, you end up with that same number of 23.5 newtons. So you do indeed find that the tension force is the same no matter if you calculate it from the perspective of M1 or M2. You just have to be a little bit careful about how you set it up. Okay, hopefully next video we'll have some tougher problems.